Hello, everybody. In today's lecture, we're going to talk about persistent homology. Specifically, we're going to touch on some of its computational underpinnings, as well as some of its applications. Throughout the lecture, you will find 4 short questions regarding the content that we're going to see here. Please take a moment to stop and think about these questions. Before we get started, I wanted to begin by going over 3 themes that emerged during the question and answer session from lecture 14, specifically questions that you guys asked through the in-class activity. So the 3 themes that emerged were computing homology via the matrix reduction. So a few of you wanted to know a little bit more about the sort of inner workings of the algorithm. Some of you also hinted at wanting to talk about interpreting the homology computation once you're done with step 1. And then finally, some of you indicated that you wanted to know about how the field of coefficient matters and sort of how does that change the interpretation of the homology computation. So I sort of pulled most of your questions into these 3 sections, but if I didn't get to your question here, please feel free to ask again during office hours. So again, the first type of questions we got were regarding the computation of homology via the matrix reduction algorithm. So here's the first question. What are the initial empty entries in the boundary matrices? Are these entries 0? The answer to your question is yes. For example, take the following simplicial complex. So it's got 3 vertices, u0, u1, and u2. It's got 3 edges, tau 0, tau 1, tau 2, and we're going to orient them in the usual way, using the indexes to indicate the direction of the edge. So if this is our simplicial complex and we wanted to compute delta 1, the first boundary, then the full matrix would look like this, right? So tau 0 has as boundary u1 minus u0, again using the orientation, and it would be 0 here in u2 because u2 does not contribute to the boundary of tau 0. The same for tau 1 and tau 2. What we usually do is we write the matrices like this. We sort of remove the zeros because it's extra information that we really don't need to continue with the reduction. Or that, you know, if you wanted to, you could reproduce by filling all the empty slots with zeros. So that's the answer to your question, yes. Empty entries mean 0. Now the second type of question that we got looks like this. How do row or column operations work? How do the indices change depending on whether it was a row or a column operation? So this is a question regarding the inner workings of sort of the reduction algorithm. I think it's best explained with an example. So think of a matrix that looks like this, 2 by 3 matrix. So these matrices, we can think of them as representing some sort of linear operator. The domain of the operator has dimension 3. And let's say that it has as bases x0, x1, x2, and the bases in the codomain say that is y0 and y1. What this matrix is telling you is exactly how the linear operator T that is represented by this matrix, how it maps basis elements in the domain to basis elements in the codomain. In particular, each column is telling you how the image of, let's say, x1 through your linear operator T is going to be given by this scalar times this basis element plus this scalar times this basis element. Similarly, let's say for x2, is saying that T will send it to this scalar times this basis element and then plus this scalar times this basis element. So let's say that we want to analyze, for example, how column operations work for this matrix. As an example, let me take column 1 and replace it by column 1 plus a constant times column 0. Notice that I'm using Python indexing notation. In other words, this is the 0th column, this is the first column, and this is the second column. So if we go ahead and perform this operation to this matrix, the result will be the matrix that appears on the right? So I'm taking my column 1 and I'm replacing it by column 1 plus C times column 0. Notice that I went ahead and added y0 and y1. So these are going to be the basis elements for the codomain. Column operations only change the basis in the domain. So that's why I'm leaving this blank and I put y0 and y1 here. Our goal now is to understand what should we put in here. What are the basis elements that sort of make this matrix in a way consistent with what we had before. So if you look at the first column of the transform matrix and you compare it to the first column of the original matrix, then one thing that you could say is, okay, still what I'm saying here is that x0 is going to a0, 0, y0, and a1, 0, y1. This is still consistent with the information we had at the beginning. Now, if you have the second column again, if you look at it here and you look at it here, you will see that you still have the same information. The challenge now is to understand what is the element or what is the basis element that should be in here in this column, right? So for that, I'm going to use again that the matrix represents a linear operator T, and the question really is, sort of answering T of this mysterious basis element, again, by reading the entries here, is saying that is this scalar times this basis element, y0, and then this scalar times this basis element, y1. So that's what we have here. So a little bit of algebra will tell you that we can also rewrite it in this fashion. And now it's hopefully much simpler to realize that, this first term is exactly the second column of the original matrix, and that this element here is C times the first column, right? Or the 0th column, rather. Again, we're using Python indexing notation. So we can go ahead and replace this question mark by this vector, right? So if you do T of x1 plus C x0, that is exactly the same thing as what I have here on the right-hand side. So what that tells you is that the mysterious element should be exactly that, x1 plus C times x0. To summarize, when you do column operations, and let's say that you're changing the kth column by taking the kth column and adding to it C times the jth column, the result in the basis in the domain is exactly what I have here. It is changing the kth basis element by the kth basis elements plus C times the jth basis element. In other words, what you're reading here in the basis side is exactly the same thing as is happening in the operations between the columns side. Okay? Let's think about rows now, because rows get a little bit more complicated. So let's say that you do the following operation. Row 1, you replace it by row 1 plus C times row 0. Let's go ahead and write down our matrix here. So I went ahead and did the 0th row times C, and I added that to the first row. So now, again, the basis in the domain, meaning x0, x1, and x2, has not changed, right? The row operations are only going to change the basis in the codomain. And then, similar to the analysis we did before, the question is, what do I put in here? Like, what basis elements do I put in here so that when I do the sort of multiplication, so this scalar times whatever I'm going to put in here, then this scalar times whatever I'm going to put in here, I should recover the same information that is encoded in the first matrix. So again, a little bit of algebra will tell you that the right things to put in here are exactly this. In other words, that if you do A0 times this first element, and then if you do this other entry times the second element, it'll be the same thing as if you did A00 times Y0 and then A10 times Y1. So what this is saying now is that if you take the kth row and you replace it by kth row plus c times the jth row, what is actually happening is that you are changing the jth basis element to be sort of the kth basis element minus c times the jth basis element. So it's got sort of an inverse feel to what the order of the operations were. So in the row, in the operation side between the matrices, I'm operating on K. In the basis side, here I end up operating on J. Here I'm adding C, and here I'm subtracting C. So it's got this sort of inverse field, it's inverse field when you're doing row operations. So just to summarize, when you're doing column operations, these are easier to remember. These are you do exactly what the operation does to the basis elements in the columns. But when you look at the rows, what you're doing is you're inverting the operation. In other words, you're switching the roles of K and J, and instead of adding a multiple, you're subtracting a multiple. The next question we got was, is the algorithm, what is actually the algorithm for matrix reduction? Are these operations ad hoc? The answer is actually no. There's actually an algorithm for reducing these matrices, even though it feels like we're doing things in an ad hoc manner. I would like to point you to this really good blog post by Jeremy McKinnon, and you can find the link here at the bottom right of the screen. So in these sort of very nice blog post, he goes in detail over how to compute homology. The part that was sort of the most interesting to me was that he's doing everything over the rational numbers, right? So it's going to be with field coefficients, as we know how to do. And just to give you an example of sort of things that he covers, let's use these Simplicial complex that he also uses in his example. So he takes the Simplicial complex, creates the boundary matrices as we also do, delta 2 and delta 1. And then he actually presents code for the operations that are going to be involved in the reduction algorithm. And so very nicely written in sort of NumPy notation. So he defines the elementary operations like swapping rows or swapping columns, the idea of adding a constant times a row to another row, or a column times a constant to another column. And then sort of here he's sort of saying how to affect sort of the basis elements in a way. This will be more sort of apparent in the next slide. So here he actually writes in detail an algorithm for simultaneously reducing two matrices A and B. In our case, the matrices of interest are going to be delta n, the n boundary matrix, and B is going to be delta n plus 1. And then what he starts is by first checking that they have the right dimensions. And then what he's doing is essentially following the same idea of Gaussian elimination. In other words, looking for pivots and then using those pivots to eliminate whatever is to the right and to the bottom of them. And he's also keeping track of, in particular here, in this last part, he's keeping track of how to do the inverse operations on rows or columns depending on what operations you did. So if you go back to one of our first questions on how do row and column operations work, you will see the similarity to what is here. At any rate, I really recommend you going to this blog post, read it and go through it, and I guess more relevant to what we're doing, get the code. I mean, he's got these available on GitHub, so you can get it and play with it. Now, the next set of questions have to do with interpretation. So here's a question that we got. Is there any relation between the number of cycles in a simplicial complex and the number of basis elements we get for the kernel at the end of matrix reduction? Does this number depend on the field over which we're computing homology? The answer to both of these questions is yes. There is, of course, a sort of a close relationship between the number of cycles that we're going to get and the kernel of the matrix. So here's a, a figure from the book of Herbert Ernst-Gruner and John Herrer, Computational Topology. And here's how the reduced boundary matrix looks like. So here we have the rank of the cycles, right? So the number of columns we're going to get in here are going to be is going to be the dimension of the cycles, right? So it's going to be the dimension of the kernel. Now, in principle, the cycles are, again, linear combinations of all these columns, right? So for example, if you're doing things over a field and you field is like R or the complex numbers, you know, an infinite field, then you're going to get infinitely many linear combinations, right? For example, take this vector here that gives you the kernel and multiply it by 1, then by 2, then by 3, by 5, by 10. So all of those are going to give you elements in the kernel, meaning a cycle. So it is in that sense that, you know, if your field is infinite, then you're going to have infinitely many cycles because you get infinitely many linear combinations. But if your field is finite, then you only get finitely many combinations of these guys, right? So that, in essence, determines how many cycles you're going to get. And as we've seen before, computing these matrices highly depends on the field that we're using, right? The operations change a lot depending on what field we use. Now, following with this interpretation of the homology computation, so we have the following question. Over Z, sometimes we have homology like Z cross Z2. Is this type of construction possible? Is this type of structure possible over other fields, like Z map P or the rationals, the reals, or the complex numbers? The answer is not really. When you compute homology of a simplicial complex and you do it over a field, what you get in the end is a vector space. So what does that mean? It means that this guy is essentially going to be the same as some sort of product of the field with itself some d times, and d is the dimension of this vector space, right? So again, this is a vector space. Everything we're doing is finite. Our simplicial complex is finite. So this is going to be a vector space of finite dimensions, say dimension d. And as a vector space, it's going to be isomorphic to f cross f cross f cross f cross f d times. And that's it. That's all we can get, right? We don't get this variety of terms that we got when we did homology over Z. And this is regardless of what field you put in here. The number of terms may change, as we've seen before, for example, using RP2, but the idea that you just get the field repeated some number of times, that is not going to change. Now the next question says, over the integers, we could understand some basic properties of the shape by looking at these numbers, like how many holes we had, how the holes are merging as we zip over slices. I guess here is asking about persistent homology already. How does this inference look like over other fields? So again, over a field, you know, your homology is just going to look like the field cross itself some number of times, and that number is exactly the dimension of this vector space. The interpretation is that you're getting d non-homologous holes of dimension n, right? So the number of factors that you have in here is the number of holes, and the dimension that you have in here is the homological dimension, sort of the dimension of the hole that you're measuring. Here's an example. So say that you have the torus, right? There's S1 cross S1. And if we compute its homology over a field, F, we're going to get that in 0. We get something isomorphic to just F, to the field. right? So this has dimension 1 because the space has only one connected component, which is what H0 is measuring. If you do H1, you're going to get 2 copies of the field, right? So this is saying that we have 2 non-homologous holes in dimension 1, right? And what are the holes? Well, this is one of the holes, and then this is the other hole, right? If we now do H2, then we get a vector space of dimension 1, right? So we only have 1 copy of F. So this is corresponding to the 2-dimensional hole that the torus itself describes. The torus is simple enough that regardless of what field you use in here, you're going to get the same answers, meaning the dimensions that you get in here are going to be the same. But we've seen with other examples, for example, with RP2, that depending on what field you choose, you may get different answers. For example, if you use Zima2, then in dimensions 1 and 2, you get Zima2 again. But if you do coefficients in Zima3, then you get 0. So this is to say that your space may be complicated and that different fields may detect different information. The final type of question we got was, does the field of coefficients matter? The answer is yes. It's certainly yes. We've seen examples of it already, but I think this is going to become much, much clearer during the computational activity that we're going to do on Wednesday, March 18th. So stay tuned. Now, what I wanted to talk about today really is persistent homology, sort of computationally what it means, and some of its applications. So going back to this picture of data, right? So we have a finite metric space. These are the points in our data. And we now know how to compute topological descriptors of the shape. So for example, if we were to compute Betty 0, we would get that is equal to the number of points in our data set. Why? Because the data is completely disconnected, right? There are no bridges joining the points. And similarly, if you were to compute Betty 1, you would also get 0. The reason is because it is not possible to draw a continuous cycle along the data set. So the picture that we've developed thus far is that we may start with a data set, but it is then possible to build simplicial complexes that approximate sort of different topologies at different resolutions. So for example, here we're building many simplicial complexes, and what we're doing is we're changing the scale at which we join points with edges, fill in triangles and tetrahedra. At the beginning, all the points are disconnected. But then as the scale parameter starts to grow, more points start to join until some cycles start to form. And one would say that at this point right here, that the sort of circular topology of the data has been captured. But one can continue, increasing the scale, and then more edges will appear, more triangles will be filled, more tetrahedra will be filled in as well, until the data has been, or rather the simplicial complex has lost all its holes. So the multi-scale picture that emerges is that we have, for example, our data set, and we're approximating it by simplicial complexes at different scales, right? And as before, we can compute topological descriptors of it. For example, we can compute the first homology of the spaces of the simplicial complexes, but now we're going to do it over a field F. And just to remind ourselves, this is a vector space, and its dimension captures the number of one-dimensional holes in the space. So for example, here we have this little hole in dimension 1 right here. So our homology would have dimension 1, right? So 1 copy of the field corresponds to one hole. Similarly here, we have also one copy of the field because we have another one-dimensional hole right here. And then finally here, we have also one copy of the field because we have this one-dimensional hole. But as we've seen before, when we move from left to right, one could say that the hole that we have represented by this copy of the field, namely this guy right here, when you move it over here, is filled in. In other words, it sort of goes to zero, it disappears. We're gonna make these a little bit more transparent in a minute. And then similarly, the hole that is captured here also goes to zero. It sort of dies entering this guy. So we have three copies of the field at these three different scales, but it is not the case that they correspond to each other. They rather sort of disappear as you move to the right. One tool that we've already seen when thinking about homology, but with z coefficients, with integer coefficients, was this idea of simplicial maps and the linear maps that they induce. Over fields, we have the same information. So we have this idea of simplicial maps and induced maps. And again, we're going to mimic exactly the same construction we had before. So say that you have a simplicial map F from K to L to simplicial complexes K and L. Then, as before, we have that F induces this map F sharp, but now at the level of chains, of n chains. So we've sort of defined these before, and we know that this is a vector space, and this is another vector space. The way F sharp is defined, well, it takes an n chain, and it operates by first pulling out the scalars lambda and operating directly on the simplices. So here the lambdas are elements of the field, and the sigmas are n simplices in the complex. And then the way F sharp is defined on each simplex, well, it is defined as 0 if we lose dimension when we apply the simplicial map F. In other words, if this has sort of dimension less than n, and if not, it's defined as plus or minus 1, depending on whether or not F sort of switches the orientation of sigma. So we've already seen this picture before with coefficients in the integers in Z, but now what emerges is that we actually have a linear transformation. So F sharp, in fact, defines a linear transformation from this vector space right here to this vector space right here. And the fact that it is linear is essentially a product of its sort of definition, okay? So we have that given a simplicial map between these two simplicial complexes, it induces these linear transformations between these vector spaces of chains. In particular, you can think of this guy as a matrix, if you really wanted to. So now we have the F sharps, and just as before, we have that the F sharps commute with taking boundaries. Remember that the way we showed this was a completely combinatorial fact at the level of simplices. And if it holds for simplices, then it will also hold for n chains with any coefficients that you put in here. We still have this relation, and what it implies is that the cycles are taken by F sharp to cycles in L, meaning, again, cycles in K. If you apply F sharp to them, you're going to get cycles in L. And similarly, if you take boundaries in K, you're going to get boundaries in L. So both of these facts come out of these simple formula. And just as we did with integer coefficients, we can now define the F star maps between these between the homology vector spaces. And we do it as we did before. You take the class of, let's say, zeta in this homology, and what you do to it is you take the class of F sharp of zeta. So zeta here is a cycle. And F sharp is sort of the linear map that we had before. The important fact, and this is the thing that we're going to use again and again and again, is that F star is in fact a linear transformation between these two vector spaces, right? So again, if you really wanted to, you can think of it in terms of matrices, right? So if we can find a basis for this vector space, and we can find a basis for this vector space, then this F star is essentially just a matrix, okay? Let me give you an example that we've actually already seen before. So let's take these two simplicial complexes, K and L. So K is just this hexagon, and L is just this triangle. The map F, the simplicial map we're going to take, is given on vertices as follows. It's going to take uj, and it's going to send it to V and J mod 3. So what does that mean? It means that U0 goes to V0, right? 0 mod 3 is 0. 1 goes to V1 because 1 mod 3 is 1. 2 goes to 2, and then 3 goes to 0 again, right? Because 3 mod 3 is 0. 4 goes to 1. 5 goes to 2, and then U0 again goes to U0, as we have said before. In other words, F, the simplicial map F, is taking this hexagon, and it is wrapping it around this triangle 2 times. Okay, so that's what it is doing. We're going to take the typical cycle that we would take in here, right? So use V0, V1 plus V1, V2 minus V0, V2. So this is the typical cycle that generates the one-dimensional homology of this simplicial complex. And zeta, we take the corresponding cycle, from U0, U1 to U2 to U3, U4, U5, and U0 again. So let's look at the F star map at the level of homologies. We already did the case of integers. We did it before in a previous lecture. And it is useful to remember again how the story goes. So both of these homologies turn out to be isomorphic to Z, to the integers. And the idea is that we're letting, for example, here in K, we're letting zeta correspond to the number 1, right? So saying that I go around zeta 1 time. And then in the codomain, I have zeta prime identified with 1, again saying that I go around zeta prime 1 time. If you look at F star, right, of the map induced by F, then what it is doing is it's sending this cycle, zeta, it is sending it to 2 times zeta prime, meaning I'm going to round this guy 2 times. And this is all sort of out of the algebra. One can sort of track step by step, the definition of F sharp in terms of F star in terms of F sharp, and so on. Now, let's see what the story looks like when we now take coefficients in Z mod 2, right, in the field Z mod 2. So again, the two homologies are Z mod 2, and here are the corresponding generators, zeta for K and zeta prime for L. If we look at F star, now the story that we get is that it is going to send zeta, namely the generator in K, to 2 times zeta prime, the generator in L, but since we're doing everything modulo 2, then we remember that 2 is actually equal to 0, right? So modulo 2, 2 is equal to 0. So in fact, what F star is doing is it's killing this class zeta as I go from left to right, okay? So this is an interesting behavior, right? It's not that the class is a sort of, is bounding something interesting when I go from left to right. It's not that it's becoming a boundary in any interesting way, but rather it is just sending it to a multiple that makes it 0 just for algebraic reasons, okay? Now, if we do the same computation, but now instead of modulo 2, we use modulo 3, right? We use the operations mod z mod 3, then we get that, zeta still goes to 2 times zeta prime. But the important thing to notice is that now 2, at least in z mod 3, is equal to -1, right? So 2 is congruent to -1 modulo 3. So in fact, zeta, which is, going around this direction, is going to zeta prime, to minus zeta prime, so it's going around this direction. So it is sort of interesting, and it's important to remember how the algebra may change the geometric intuition that we had before. So to summarize, every time we have a simplicial map between simplicial complexes, we get a linear transformation given by these F stars between the homology vector spaces. So now is the time to try to think about the effect of choosing different bases, both in the domain and the codomain of the F star maps. So as an example, let's assume that we pick different bases for the domain and for the codomain. In this case, the domain, meaning the homology of K, has, let's say, dimension 3, and the homology of L has, let's say, dimension 4. As I said before, if you have a linear transformation and I fix bases for the domain and bases for the codomain, then I can express it as a matrix, right? So this is exactly the same thing as matrix multiplication by some, let's say, 4 by 3 matrix. Now, the thing to sort of remember is that once you have a matrix, you can do operations to it, right? You can do row operations, you can do column operations. In particular, you can do Gaussian elimination to the matrix. Let's say that Gaussian elimination to this matrix results in the following choice of bases, right? So we went from the purple bases to the blue bases. And let's say that the matrix that I obtained by doing Gaussian elimination now looks like this, right? So if you read off the matrix entries, right? And again, Gaussian elimination will always, if you put it in row-reduced echelon form, it'll always have 1s and 0s as entries, and it'll have unique pivots per column. So for example, here he's saying that the first basis element, meaning this guy, is going to the first basis element, meaning this guy. So pictorially, one can write that matrix in this form. And this is sort of a very simple but important fact that we're going to leverage now to think about persistent homology and estimating the homology of data. Okay, so going back to our picture of a data set on the left, and then the different complexes that I may use to describe its underlying topology. So the question that we've always had is, how do we pick an appropriate scale at which to look at the data? And the answer that we've been sort of inching towards is this idea that we should just look at all scales at once, right? Look at all the different epsilons, all the different sizes of balls, of complexes that we're using to approximate our data. So if we look at all scales at once, then what that is going to give us is this family of simplicial complexes, K0, K1 through KL, that are again describing the data at different resolutions. Now, for each one of these complexes, we can compute their homology vector spaces. We could, of course, compute their integer homology as well, but as we're going to see now, doing it with field coefficients gives us some advantages. As we said before, now that we have vector spaces here, we can find bases for them. So let's say we have, again, the purple dots represent the basis of each one of these vector spaces. And the thing to remember is that not only do we have simplicial complexes here at every scale, but rather they are related via simplicial maps. So for example, in constructions like the Reeves complex or the or the Czech complex rather, we have that at one scale, let's say at epsilon 0, you get a complex that is contained in the complex at the next scale. And this is contained in the complex at the next scale. And this is contained in the complex at the next scale. So we get these simplicial maps relating the complexes at all the different scales, right? And perhaps these are inclusions, like these K0 being included in K1 if these are Reeves complexes of the same data set, but perhaps they're just simplicial maps, So once we have the simplicial maps, we can look at the star linear transformations that they generate at the level of homology vector spaces. And now we can start to keep track of how these basis elements are being mapped through these homology vector spaces. So let's say that for the first chunk, we use these bases to pick a matrix representation of the first star operator of F0 star. As we've seen before, it is possible to, for example, make a change of bases for the first two in such a way that the basis elements correspond. Now, here's where things are very nice when we use field coefficients. What is true, and it is non-trivial to see it, but it is certainly true. Once you do field coefficients, it is actually possible to change all the bases at once, so that the basis elements correspond in the fashion identified by the arrows. In other words, these bases are compatible in the sense that a basis element like this dot is going to another basis element. Two different basis elements will always go to two different basis elements, or a basis element will map to 0, right? So that is the magic of persistent homology, that not only can one sort of change the bases in two of these vector spaces at one time, for example, doing Gaussian elimination, but rather that there is a procedure, again, there's an algorithm that looks very much like Gaussian elimination that updates the bases in all of these homology vector spaces at once. The algorithm and the breakthrough for actually doing this was described in this paper, Computing Persistent Homology by Afra Zomorodian and Gunnar Carlson. And these have opened the floodgates, right? So because now there is sort of a well-defined algorithm for changing all these bases at the same time and putting them in a correspondence that allows you to track how homological features change from left to right, or in other words, across scales. And it allows us to paint this picture of barcodes as what captures the persistent homology of data sets, right? So the idea is that, you look at your data at different resolutions, you compute homology, for example, in dimension 0, 1, 2, and beyond, and then you, by doing that change of coordinates across all these vector spaces, you're able to put homology generators in correspondence with homology generators in such a way that you can track how the homology of the spaces is changing. So here is just one example that hopefully encodes most of what we've seen in the course. Here I'm showing you a torus, and I'm showing the Betty numbers, right? So this count the number of holes roughly in each dimension. I've also generated a point cloud sampled from this torus, and I've created the barcode for the Reeves filtration, sorry, for the Reeves complex at different scales in this point cloud. And the barcode that emerges is what I'm showing here on the lower right. The thing to notice is that you get all these sort of small bars that appear and disappear, right? So those are, for example, here we're looking at the barcode in dimension 1, homological dimension 1. So this is saying that there are some holes, some loops that appear and then they get filled in rather quickly. If you look at these longer bars, these indicate homological features that appeared at the beginning and last a while in the evolution of the complexes. The same here in dimension 2, right? So you have this homological feature that lasts for a while, and then you have these other sort of two-dimensional features that appear and disappear rather quickly. So if you sort of compare the long bars that you have in each dimension to the Betty numbers of the space, you will notice that the long bars indicate the underlying homology of the space from which the data was sampled, right? So here you have one connected component because Betty 0 is 1, but the barcode in dimension 0 also has only one long bar. Betty 1 is 2. Here in the barcode, you have two long bars. Betty 2 is 1, and here in the barcode in dimension 2, you have also one long bar. So the barcodes are supposed to recover the topology as measured by sort of the Betty numbers in lower dimensions. So now I would like to show you some applications of persistent homology to interesting data sets. During the computational activity, you will have the opportunity to apply persistence to several data sets by yourself. So you will be able to compute and actually see how the algorithms work. But for now, let me just give you a preview of what is possible. So the application I'm going to start with is to computer vision, to the problem of teaching computers how to see. So there's this very, very nice paper from the 1990s by Reynagel and Zador, and they're interested in figuring out what is it that humans look at when they see an image. So what they do is that they follow the regions where the eyes are sort of focusing the most. So the dots are places in the image where a human sort of subject is looking at the image more intently, and then the lines are showing how the eye movements sort of jump from one place to the image to the next. And what they sort of start seeing is that areas with high contrast, meaning where there are sort of breaks or edges, are places where the human eye tends to concentrate the most. A natural question would be, if we look at a natural scene, meaning a picture of the world, one question could be, if we look at the high contrast regions, meaning the areas where we're going to focus our attention the most, what is the statistical structure of this set of patches? So going back to Jan van Hateren, there is this sort of classical data set of images sort of around town. And these are 4,000 images of just, nature, a city and their surroundings. And these are sort of high quality 4,000 grayscale images. So what one can do is look at these images and extract from them the set of high contrast 3x3 patches, right? So 3 pixels by 3 pixels. So for example, if you look at one of these patches, a 3x3 patch, then you can turn it into a matrix where, for example, the color black is represented by -1, the color white is represented by 1, and all the grayscale values in between by other numbers, right? So you can turn these images, for example, these 3x3 patches, into 9-dimensional vectors by just concatenating the columns, right? So this would be the first column, this would be the second column, and this would be the third column. So each 3 by 3 patch is giving us a point in R9. What Lee, Peterson, and Mumford did in 2002 was to consider the following data set. They're going to look at all those 3 by 3 patches from the Van Hatteren image data set. They're going to consider only the ones that are high contrast. They're going to intensity center them, and they're going to contrast normalize them. Intensity center means that they're going to consider 2 patches as being equivalent if they differ by an additive constant. All right, so they are, in other words, subtracting the mean. That's another way to think about it. Contrast normalized means that 2 patches are going to be considered the same if they differ by a multiplicative constant. In other words, they are sort of normalizing by contrast. That's another way to think about it. So here are some of the patches that emerged from this experiment. Again, each one of these patches was a 3 by 3 patch with high contrast that was centered and normalized. So now we took these 2 relations. So these are 2 linear directions, right? So here we're subtracting the mean, and here we're normalizing. So the effect that that has is it puts all the data points, all the 3 by 3 patches that we had, and it puts them on the surface of a 7-dimensional sphere. Why? Because the first linear transformation sends your patches from R9 to an 8-dimensional subspace, and then the second relation normalizes something in 8-dimensional space to a sphere of dimension 7. And there are 2 facts that are important here. It turns out that the data set that is generated in this fashion, the patches, it fills out the 7 sphere completely. But not all the regions in the 7 sphere are equally densely populated. So one question is then, what is the shape? What are the properties of the regions in the sphere that are more densely populated? So this is a question that Carlson and others sort of tackled, almost 12 years ago, and they thought of the following. So they said, okay, let's look at the regions that are most important in this data set, and how do they do it? How did they do it? So they said, okay, let's fix an integer k, and we're going to consider this delta k, which is going to measure for each v in the data set the Euclidean distance from v to vk. And what is vk? Vk is the kth nearest neighbor of v in M, right? So it's looking at distance from v to its kth nearest neighbor in the data. So one thing to notice is that if you look at 1 over delta k, this is of course a measure of density, right? So if this number is very small, it means that v has a lot of neighbors around it. So it means that it's pretty dense, and conversely. So what they looked at in this paper in 2008 was to look at the regions XKP, which are the top p% given these density estimator for all sub k, right? So these are some of the most important regions in this data set that now lives in the 7-dimensional sphere. And here's how what they found. So, for example, if you look at the top 30% densest points in the data with respect to computing distance to their 15th nearest neighbor, then a simple PCA of that sort of region of the data looks like this. So I just did here sort of 3-dimensional PCA, nothing complicated. Remember that the original data set, the entire set X, sort of occupied the entire 7-dimensional sphere. But when you look at sort of these dense regions, they start to have other types of structure. So in particular, if you compute the persistent homology, right, the barcodes, it turns out there are 5 persistent bars in dimension 1, right? So there are 5 cyclical features in that data set. And the model that emerges is the following. It's what is called the 3-circle model. So what is the 3-circle model? The 3-circle model is made up of three circles. There is a green circle here, there is a blue circle here, and there is also a red circle. Now, the green circle touches the blue circle at 2 points, and it also touches the red circle at 2 points. But the red and the blue circles do not touch each other. So you have three circles, and the actual patches that occur on each circle are as follows. So the red circle essentially has patches which are all horizontal, right? They all look horizontal, and they sort of provide this transition from sort of linear gradients, right? Something that goes from dark to medium dark to light, to these sort of quadratic type of gradients, and again back to linear, and then back to quadratic. And then the thing to notice is that the top here is the same as the bottom. So this really is a circle, right? The blue circle is also made up of transitions from quadratic to linear, and then quadratic and then linear. But now all these patches look vertical, right? Notice that there is no intersection between blue and red. And the green circle, which starts here, goes all the way up to here. And now notice that this guy here is the same as here at the bottom. And then if you go to the right, it'll be this guy the same as that guy. So this green is really a circle. So it intersects the other two at 2 different points, right? So the green circle is essentially capturing all the linear gradients at different orientations, right? So you can see how the orientation rotates as you go around the green circle. So this is the 3-circle model, and what one can check is that this really has 5 holes, right? So for example, these here is one of the holes that I'm marking over here. This guy, for example, here, right? This is another one of the holes. So one can count essentially 5 holes in this 3-circle model. Even though it is 3 circles, the way it sort of combines gives you 5 generators in homology in dimension 1. So here's another portion of the data. So now they take the sort of a different, sort of even denser region of the data, even more important region of the data. And what they find is that by computing persistence with Z-mod 2 coefficients, they find the space that is connected, right, this dimension 0, it's got 2 holes in dimension 1, and then it's got 1 hole in dimension 2. If you remember the torus, you will think, oh, this looks exactly like a torus. But actually what happens is that when you change the coefficients from Z-mod 2 to Z-mod 3, this class here in dimension 2 disappears, and one of these classes also disappears. So what it says is that it's not a torus, right? So here is one instance where changing the field of coefficients really helps you determine what the space is. And there is one space we already know that when you change the field of coefficients will change its homology. We haven't seen it in the course, but it's time to, or at least we haven't computed its homology, but we know what the space is. And the space is the Klein bottle. And here's how the Klein bottle parameterizes the set of patches that are likely to appear in this image data set. So it essentially completes the 3-circle model that was only looking at sort of vertical and horizontal circles in this vertical direction here, and it essentially adds all the intermediate rotations. And what you will notice is that the bottom now is exactly the same as the top. So that would form a cylinder, and now the left is the opposite of the right. So this is really a Klein bottle describing these patches. So what the conclusion is of this sort of 2008 paper is that most high contrast patches of sort of small size, let's say 3 by 3, from natural images accumulate around this space with the topology of the Klein bottle. And the way this space was found was again by looking at the data, computing persistent homology, and finding a candidate space that would describe the homology that you're seeing. What I'm going to show you now is one technique that one can use to sort of leverage this model of natural images. And the application that I'm going to show you is to texture classification. So what are textures? So these are images of objects that have sort of statistically similar patterns as you move across the image. And here I'm showing you sort of 4 different textures and 4 different textures at a different rotation angle. So what is the idea that we're going to use in texture classification? So if I give you one particular image, and then I take its 3 by 3 patches, now we know that most of them are going to be accumulating around the Klein bottle we found. So the idea is going to be to represent an image, a texture image, as a density function on the Klein bottle. In other words, depending on what patches I'm going to get in here, I'm going to get some distribution around the Klein bottle, and potentially different textures are going to end up in different densities. The second idea is to use sort of ideas from Fourier analysis, but now in the Klein bottle, to represent probability density functions on the Klein bottle via Fourier-like coefficients. So this is something we did like 8 years ago. And here's how it works. So you start with an image, right? And again, you look at these 3 by 3 patches, and you look at how they accumulate around the Klein bottle. So for this image, for example, this is the picture that emerges. The picture in colors is the density, sort of hotter regions is sort of more dense. And here's the Klein bottle just for reference. What you will notice is that the hotspots are located exactly in the sort of vertical regions of the Klein bottle, which is sort of consistent with how the image looks like. Next, what we do is we compute the Fourier-like coefficients of this density function. So now we can use this vector of coefficients to do image classification. So we classify the image by looking at the different Fourier coefficients, right? So here's a data set of sort of different textures at different rotations. And what I'm showing you here at the bottom left with different colors, so each color is a texture, it's a different texture, different colors mean different rotations and different conditions, is that sort of using these Fourier coefficients really sort of captures the different textures in this data set. And at the time when we did this, and we sort of compared it with other sort of classifiers, we obtained sort of reasonable classification results compared to sort of the state of the art at the moment. But this is sort of a completely different scheme where one is actually using the shape of the space to do classification. Now, going back to this representation of persistence homology as barcodes, right? So we have all these bars that start at some point, let's say B, and end at some point, let's say D. Notice that each bar can be replaced by a point with coordinates B, D, right? So a bar that starts at B and ends at D can be replaced by a point of coordinates B, D. So there are sort of these two pictures of persistent homology. One is the barcode, which I like to think of as this idea of consistent choices of bases, and the persistence diagram, which is sort of this scatter plot where each dot corresponds to a bar. Now, each dot in the scatter plot in the persistence diagram means that the x-coordinates is when the topological feature is born, the birth time. The y-axis is when the topological feature dies, the death time, and D minus B, death minus birth, is the persistence of the topological feature, right? So in a recent paper, we used persistence diagrams or persistent homology to do protein classification. So what is the story? We take different proteins and we describe them by the location in Euclidean space of their atoms. So we take all the points that we get from each protein in R3 and compute persistence diagrams for the Rips complexes, right? So I mean, we don't expect to get, a long persistent bar or a point with high persistence, but the distribution of points somehow captures the shape of the protein, okay? And the idea is we're gonna train machine learning algorithms to do classification of the proteins by doing classifications on the persistence diagram. So for these, we used this protein classification benchmark data set, which is sort of a widely known sort of data set for protein classification. What we showed is that using sort of some topological features, sort of these are the lines in green, we obtain up to 98% classification accuracy over several tasks in classification of proteins. And this sort of bumps up the previous known results from sort of 82% accuracy to our 98% accuracy. So the goal of this example is to show that not only can one use persistence, and in particular barcodes or persistence diagrams to capture and infer the topology underlying a data set, by looking at the long bars, but that also sort of just the distribution of topological features as captured by the persistence diagrams is useful for tasks like classification and prediction. We'll see more of that as we move forward. But for now, let me just wrap up by saying that today we talked about persistent homology, the idea that the barcode really is a representation of sort of changing bases simultaneously in all the scales, in all the simplicial complexes, and that the magic is that one can do these all at once. Next time in the computational activity, we're going to put these ideas to the test, and we're actually going to compute persistent homology for some data sets. See you next time.